Hi, my name is Ruojia and I am from the Hybrid Body Lab at Cornell University. Today, I am so excited to present my project, Weaving a Second Skin, exploring opportunities for crafting on-skin interfaces through weaving. Weaving as a practice dates back to 2000 BC, and it has been adopted in cultures all across the world as a means of textile production and as a creative art form. In its long history, it's developed to be incredibly rich in structural, textural, aesthetic, and cultural expressiveness. So why are we interested in weaving an on-skin interface? Well, current fabrication methods for on-skin interfaces, such as laser printing and stenciling, are based on simple rapid prototyping or craft techniques that, while they afford function, they typically only achieve a single function per device. On the other hand, weaving has 2- and 3-dimensional structural capabilities that support more complex circuit typography. And in addition, weaving easily integrates a broader range of materials, which are difficult to incorporate with the current methods. Lastly, aesthetically speaking, while current fabrication methods enable color and graphic customization, they do not offer the same rich textures and patterns that weaving does. With woven skin, we are merging the structures and functions of e-textiles with the slim form of on-skin interfaces. Therefore, we build upon related works from both of these fields. Current fabrication methods for on-skin interfaces include screen and inkjet printing, stenciling, and embedding. They can achieve a slim form factor, be rapidly prototyped, and afford functions such as touch input, visual output, and haptic feedback for seamless and always available interaction. However, these methods have structural and material limitations that weaving can overcome. The other field that has inspired woven skin is e-textiles. Many e-textile works rely on conductive threads to enable function at a surface level, such as with embroidery. However, we were interested in a technique where we can control the textile at a structure level to achieve a skin conformable form and support complex functions. One such technique is knitting, which has a looped and stretchable structure. However, it is limited to materials which can withstand high tension. On the other hand, with weaving, any material can be used in the weft, and its gridded and layered structure works well for textile circuits. This makes it ideal for the exploration of the first textile on-skin interface. Our contributions are woven skin, a fabrication method for adapting weaving for on-skin interfaces where polyvinyl alcohol, PVA film, plays a key role. We also present 4 case studies to demonstrate the functional capacities of woven on-skin interfaces and 4 more case studies to explore the aesthetic opportunities. Lastly, we conduct a workshop study and a wearability study. We use a research through design approach proposed by Zimmerman to create an annotated portfolio, which, as underscored by Bill Gaver's paper, can be a means for theory production to form our design space. As you can see from our 5-dimensional design space, woven skin can be fabricated using different tools and machines for different scales and levels of complexity. We identified different materials suitable for on-skin wear and the woven structures to support our functional and aesthetic dimension exploration, which I will elaborate on more later. Here's our 3-step fabrication process. First, we sketch and plan the weave based on body placement and function, prepare materials, and set up the loom. Next, we weave the device based on the function and the aesthetic design. Lastly, we apply the woven skin onto the skin using a layer of PVA film, which will adhere the device to the skin when it's dissolved. We arrived at this method through a systematic exploration of a variety of materials and attachment modes and found that using PVA film leads to the best result, and it allows the device to remain attached for more than 24 hours. Now let's look at the 4 functional case studies, which all achieve functions that are difficult to implement with current fabrication methods for on-skin interfaces. The first functional case study is a multifunctional device with capacitive touch input and thermochromic display output. This is achieved through a 2-layer woven structure. On the top layer is the display, and in the bottom layer, we have the heating circuitry. An example application is a 7-segment display where the number can be increased or decreased by touching the 2 capacitive touch electrodes. This is our second multifunctional example, where the input is pressure sensing and the output is SMA or shape memory alloy haptic feedback. An example application is a haptic feedback alarm, which has 2 input modes of firm touch and light touch. And here in the video, you can see the SMA contract to notify the user. Next, we demonstrate electrical connection across layers, or vias. The vias are made possible by the 3-dimensional capacity of weaving. In this example, an LED with wires is woven partially into the top layer and then woven into the bottom layer to be connected in parallel with an SMA spring. With vias, the LED and SMA can be activated using a single voltage source. With other on-skin processes, it can be challenging to integrate novel materials, but this is easy to do with weaving, since one unique quality of weaving is that it can integrate any material in the weft. We leverage this to weave in a novel stretchable optical fiber for bend detection. Next, let's examine our aesthetic case studies. Here we have examples of pattern and texture. On the left, we have a geometric monk's belt pattern, and on the right, a subtly textured twill. Both of these woven skin devices function as color-changing displays, combining aesthetics and function. We also demonstrate devices with unusual materials and blank space. On the left is a capacitive touch slider woven with upcycled plastic bag to give a second life to a single-use plastic item. And lastly, on the right, we present another capacitive touch slider woven in a Brooks bouquet lace, which reveals the skin underneath so that the wearer can feature their own body in the design. We also conducted a workshop study to gauge the feasibility to create personalized designs with the woven skin process and probe textile expert perceptions toward weaving on-skin interfaces. In our study, we had 3 participants who were all textile practitioners. They had 1 hour to learn the fabrication study, a day to plan their design, and then they came into the lab to weave their project for 4 hours, followed by an interview. The first result of this study is Skylar's touch sensor for the heart. Skylar is a textiles artist with 15 years of weaving experience who runs her own weaving studio. She's interested in bridging emotive qualities into her work, which inspired this design, a capacitive touch slider that can be worn on the chest for touching one's own heart. It is woven in an expressive overshot pattern where the conductive wires form both the aesthetic pattern as well as the functional touch element. And this was Skylar's first time weaving with copper wires, so she mentioned the importance of getting to know them through hand manipulation. Next, we have Quinn's device. Quinn is a textile studio assistant with 3 years of weaving experience. They describe their textile art practice as using yarns to draw or tapestry. This idea is mirrored in the function of their device, which is inspired by the childhood game of drawing on someone's back and having them guess what was drawn. The device is worn on the back so that when another person touches it, the touch input can be projected on a phone or laptop screen for the wearer to see. Quinn mentioned that they underestimated the time it would take to fabricate the device, but practicing with the thin form sped up their work process immensely. Last but not least, we have Avery, a university textile art instructor with 14 years of professional experience. Her background in knit made her interested in textural and sculptural qualities of textile. As a result, for the workshop, Avery wanted to create a safety blanket for the skin with touch capabilities and a soothing and unique tactile quality that a wearer could rub when they felt unsafe or distressed. Avery mentioned that she likes to take an improvised approach to her textile practice, so she experimented with various textures and materials and eventually chose this slim open space design with copper wire and tapestry shapes. From the study, we observed that the thin form and functional elements of woven skin was new to the weavers, but they were all able to bridge in their textile practice, and that hand experimentation with the materials was crucial for them to develop their process and design. Additionally, all the participants were excited about extending textile qualities, such as textures, to on-skin wear, particularly due to the increased closeness of textiles when placed directly on the skin. Lastly, participants compared woven skin devices to other forms such as body ornamentation and hosiery, suggesting that they're a new hybrid form factor. We wanted to highlight how in weaving, the maker can work in an intimate partnership with the materials, tools, and machines to craft the on-skin interfaces, which Devendorf and Rosner describes as co-production. In other on-skin fabrication methods, production is primarily offloaded to the machine, but weaving presents unique opportunities for the maker of the device to be more involved in the fabrication process to create more personalized devices. While weaving affords hand experimentation, it also affords scalable manufacturing. For future work, we can explore the potential for fabricating woven on-skin interfaces using digital jacquard looms for scalability and speed, which is a challenge with other on-skin interface fabrication approaches. Currently, our devices are mainly rectangular in shape due to the grid-like nature of weaving. In the future, we will explore different ways of weaving free-form silhouettes, such as the method demonstrated in this collection, Issey Miyake's A Piece of Cloth. Additionally, we want to move toward fully integrated and durable on-skin interfaces by investigating how electric components can be more seamlessly woven and worn, as well as stretchy medical-grade adhesives. In conclusion, woven on-skin interfaces can support multiple functions in a single structure and across layers, as well as integrate novel functional materials, all while offering dynamic patterns and textures. The versatility of the woven approach allows for, at one end of the spectrum, hand experimentation, and on the other end of the spectrum, scalable manufacturing. By adapting the woven craft, we expand the design potential of on-skin interfaces. Thank you so much for listening to this presentation.